Good morning, cadets. Let us solve some more numerical problems as a part of revision. Today I have chosen one problem based on condition of equilibrium. We have learned about the condition of mechanical equilibrium. A body is said to be in mechanical equilibrium if it is both in equilibrium with respect to the forces and equilibrium with respect to torques. So, equilibrium with respect to forces. What do you call that equilibrium with respect to force? That is condition of net force equal to 0. Condition of net force equal to 0. And next one is condition of net torque equal to 0. When the net torque equal to 0, then we call it as rotational equilibrium. If the net force is equal to 0, then it is said to be in translational equilibrium. So, body is said to be in total mechanical equilibrium if it is in equilibrium with respect to translational motion as well as with respect to rotational motion. So, the condition of mechanical equilibrium is attained when the body is in translational equilibrium as well as rotational equilibrium. So, for translational equilibrium, net force must be equal to 0. And for rotational equilibrium, net torque must be equal to 0. So, the first part of this question is what is mechanical equilibrium and what is the condition, what are the conditions for mechanical equilibrium. And the next part is this numerical problem. So, both together it is of 5 marks. So, I have explained what is mechanical equilibrium and what is the condition. What are the conditions of mechanical equilibrium? Conditions of mechanical equilibrium are that net force must be equal to 0 and net torque must be equal to 0. Net force, net torque, summation of all the torques must be equal to 0, summation of all the forces must be equal to 0. These are the conditions of mechanical equilibrium. Mechanical equilibrium, right? In short, I have written mechanical equilibrium. So, this is the condition of translational equilibrium. Condition of translational equilibrium. And this is the condition of rotational equilibrium. Rotational equilibrium. Now, see the problem here. The one end of a uniform rod, this is the uniform rod, the one end of uniform rod of mass 1 kg and length 2 meter is placed at a wedge as shown in the figure. It is placed at a wedge as shown in the figure. Okay. Then a mass of 2 kg is suspended at a mark 50 centimeter. Mark of 50 centimeter here from the wedge, from this wedge at the mark of 50 centimeter, a mass of 2 kg is suspended and a force F is applied. You can see this is the force of application vertically upwards. A force F is applied to the free end. A force F is applied to the free end as shown in the figure to keep the entire system in equilibrium. To keep the entire system in mechanical equilibrium. Then find the force F. What is the force required? Force F. And what is the reaction force F1? This is the reaction force on this wedge. That is first wedge. On the wedge. What is the reaction force on the wedge? Plus what is this force F? What is this force F? Which can just balance this 2 kg weight as well as 1 kg weight. 2 kg weight as well as this entire system, right? So, first we will apply the condition of rotational equilibrium, that is net torque must be equal to 0. So, net torque must be equal to 0 is also in line that the clockwise torque, sum of the clockwise torques must be equal to sum of the anti-clockwise torque. Look at this force F1. The force F1 is acting vertically upwards. So, the clockwise torque is F1 into the perpendicular distance from the center of gravity, that is clockwise torque. And this load 2 kg has a weight of 2 kg force acting vertically downwards. So if you take acceleration due to gravity as 10, it becomes 20 Newton. 20 Newton acting vertically downwards. So this also tends to turn it clockwise. So sum of these clockwise torques must be equal to the anti-clockwise torque that is exerted by this external force in order to bring it in equilibrium. So I am using this one first, rotational equilibrium, and later on to find the actual forces we will use this translational equilibrium, condition of translational equilibrium. So condition of rotational equilibrium, sum of clockwise torques must be equal to sum of anti-clockwise torques. Now, so first we will write the clockwise torque due to F1. The F1 is acting about its center of gravity. Center of gravity will be exactly at 1 meter. If this is of 2 meter, which is a uniform rod, then center of gravity will be acting vertically downwards. So if this is center of gravity, then the mass of this center of gravity is nothing but the mass of this entire rod. Mass of this center of mass is equal to the mass of this entire rod, which is equal to 1 kg. M is equal to 1 kg. Therefore, center of gravity, so its weight becomes 1 kg into 1 kg into 10, so it becomes 10 Newton. 1 kg into 10 Newton. Let us write this. Okay. So we will just write 1 kg mass. Later on, we will write that 10 Newton. Right. Now, sum of clockwise torques. Look at this. Sum of clockwise torques is given by F1 into the distance from the center of gravity is 1 meter. 1 meter. F1 into 1 meter plus one more torque is exerted due to this 2 kg force. 2 into 10, that is what I have written as 20. I am taking acceleration due to gravity directly as 10 meter per second square. 2 into 10 into the perpendicular distance. The perpendicular distance from here is 50 centimeter. Perpendicular distance from here is 50 centimeter. So 50 centimeter you convert it into meter. So it becomes 50 by 100. So this becomes the sum of the clockwise torques, which should be equal to sum of the anti-clockwise torques. There is only one anti-clockwise torque which is balancing this, that is due to force. So this force into, it is acting about this, wedge. Therefore, we have to take the perpendicular distance to be 2 meter. F into 2, this is anti-clockwise, this is sum of clockwise. So thus, if we cancel this, we get F1 into, so we will just verify. So there is a correction here. This entire weight of this rod is balanced by this wedge. Therefore, the entire weight of this rod is present at the center of gravity, whose mass is 1 kg, and therefore its weight becomes 10 meter. 1 kg into 10, that is 1 kg into acceleration due to gravity. So I have taken it as 10 meter per second square. 1 kg into 10 meter per second square. So the weight of this rod becomes 10 Newton. This 10 Newton is acting about this wedge. Therefore, I have to write the clockwise torque. Clockwise torque, I have to write that for this entire rod due to center of gravity. So first I am writing for this 10 Newton multiplied by 1 meter, because its distance from the wedge is 1 meter. 10 Newton into 1 meter plus, this is clockwise, plus 20 Newton. You can see here the weight here is 2 kg force, which is equal to 20 Newton. 20 Newton into 50 centimeter. 50 centimeter is nothing but 0.5 meter. 50 divided by 100 meter. So this becomes anti-clockwise moment. This becomes clockwise moment. Clockwise moment is equal to anti-clockwise moment. Anti-clockwise moment is given by F into 2. This entire F into 2. Because this is the wedge which is balancing the entire rod, and after keeping 2 kg force, an external force of F is exerted vertically upwards to have it in equilibrium. Therefore, clockwise moments, some of the clockwise moments must be equal to anti-clockwise moments. So, if you calculate, this becomes 10 plus, you see, it becomes 5 by 10. So, 5 by 10 is nothing but 0.5. 0.5 into 20 becomes again 10. So, thus becomes F into 2. Therefore, F is equal to 20 by 2. So, F becomes 10. So, this is how we find out this F using the condition of rotational equilibrium. Now, to find out F1, we use the condition of translational equilibrium. Net force must be equal to 0. Net force, look at this. What are the net force? One is 20 Newton, another one is F, that is acting vertically upwards. You can just write condition of translational equilibrium. Look at this. These two forces, F1 and F1 and F are balanced by 20 Newton. F plus F1 is equal to F plus F1 is equal to 20 Newton. This is 20 Newton. Therefore, we want F1. F1 becomes equal to 20 minus, let me check once again. We have to check the direction. Look at the problem carefully. Look at the diagram. 10 Newton force is acting vertically downwards. 20 Newton force is also acting vertically downwards. So these are the two forces acting vertically downwards. So net force here it becomes 10 plus 20, 30. These 20 plus 10, 30 Newton, they balance F1 and F. So I can write condition of translational equilibrium. F plus F1 must be equal to 20 plus 10, 30 Newton. 30 Newton. Therefore, I need to calculate F1. Therefore, F1 is equal to 30 minus F. 30 minus F becomes 30 minus 10. So it becomes 20 Newton. Therefore, F1 is equal to 20 Newton. So this is 20 Newton. This F is 10 Newton. You can just verify. 20 plus 10. These 30 Newton weights, 30 Newton forces are balancing 20 plus 10, 30 Newton force which are acting vertically downwards. This is how we need to solve the problems of equilibrium. Okay, now let me solve some simple problems. Very simple problem, maybe for 1 mark. Look at this second problem. An ideal fluid flows through a pipe of circular cross section made of two sections with diameters 2.5 centimeter and 3.75 centimeters. Suppose this is one circular cross section of 2.5 centimeter. There is another circular cross section of 3.75 centimeter diameter. So if this is the shape of the pipe, then find the ratio of velocities of the fluid in the two cross sections. Ratio of velocities of the fluid in two cross sections. If you take this as cross section A1 and flow of fluid as V1, and if you take this one as cross section A2 and flow of fluid entering as V2, suppose the fluid is entering and flowing like this, having a streamline flow, then we use equation of continuity. Volume of fluid entering is equal to volume of fluid leaving, or amount of fluid entering is equal to amount of fluid leaving. That is the equation of continuity. So, equation of continuity, it states that volume flux remains constant. So, A1 V1 should be equal to A2 V2. So, you are asked to find out what is ratio of these velocities. Here, A1 is cross section of this first one, where it is given by circular cross section. So if d is the diameter, then d1 is the diameter, then we can write it as A1 as pi d square by 4, because pi r square is the diameter, so I can write it as pi d square by 4, that is the A1. So in the same manner, I can write what is A2. A2 is equal to pi d2 square by 4. Just substituting this equation. Therefore, I can write V1 by V2. V1 by V2 is equal to V1 by V2 is equal to A2 by A1. A2 by A1. A2 by A1. Just substitute the value of A2. Pi D2 square by 4 divided by pi D1 square by 4. Pi cancels, 4 cancels. So you are left with D2 square by D1 square. Just substitute the values. So this becomes 3.75 diameter. 3.75 square. 3.75 divided by 3.75 divided by D1 square. D1 square is 2.5. 2.5 into 2.5. So if you cancel it with 5, so it becomes 37.5 into 37.5 divided by 25 into 25. So 5 5s are 5 5s are 5 6 are 5 7s are 35. You can see 5 7s are 35. 2 remains 7.5. So directly you can cancel with 25. So 5 ones are 5, 1.5. So 25 ones are 25, 1.5. So you get in the numerator 1.5 into 1.5, and in the denominator you are getting 1. So 2.25 divided by 1. So that is the ratio. 2.25 divided by 1. So which means this implies V1 by V2 is equal to 225 by 100. 2.25 can be written as 225 by 100. So I can just cancel it with 25. 25 4s are 25 9s are. So it becomes 9:4. So this is ratio of speeds. So when there is a narrow cross section of the pipe, the speed of wind increases. When there is a broader cross section of the pipe, the speed of fluid decreases. V2 is of the order of 4 and V1 is of the order of 9. So this is clear from this numerical problem. We will solve still more numerical problems in the next session. Thank you. Have a nice day.